NASA's James Webb Space Telescope just captured a colossal 8-light-year jet blasting out of a newborn 10-solar-mass star, so huge it stretches about twice the distance between our Sun and Alpha Centauri. Scientists say this rare superjet scales with the mass of its parent star, and it's rewriting how we think massive stars are born. I'm Naim, and today we're breaking down NASA's latest Webb result from the SH-284 nebula, how an 8-light-year plasma jet works, why it looks like a cosmic lightsaber, and what it tells us about the birth of massive stars, especially in parts of the galaxy that resemble the early universe. If you love deep space discoveries translated into plain English, hit like and subscribe. Let's dive in. SH-284 sits in the outer reaches of our Milky Way, about 15,000 light-years away, where gas clouds are relatively pristine, with fewer heavy elements. Astronomers call that low metallicity. It's important because regions like this act as local analogs of the early cosmos, before stars seeded the galaxy with heavier elements. In other words, this is a time capsule environment, a way to study how massive stars may have formed when the universe was young. When a star forms, gravity pulls gas inward, creating a rotating disk around a growing protostar. But not all infalling material joins the star. Magnetic fields act like rails, funneling part of that gas out along the star's spin axis as high-speed, tightly collimated jets. Think cosmic fire hoses made of plasma. These protostellar jets are the universe's way of saying, a star is being born right here. Webb stumbled on something rare, a massive protostar about 10 times the mass of the Sun, launching a superjet spanning 8 light-years. Most jets we've imaged come from low-mass stars. Seeing a huge, symmetrical, needle-thin jet from a high-mass star is unusual, and it shows a clear trend. Bigger star, bigger jet. At hundreds of thousands of miles per hour, the jet plows through interstellar gas, carving filaments, knots, and bow shocks, ripples you can actually see in Webb's infrared image. Those ripples are like tree rings, preserving the timeline of the star's growth. For decades, astronomers have debated how massive stars form. Theory A, core accretion. The protostar grows inside a relatively stable, rotating core with a steady disk. Jets stay aligned over long times. Theory B, competitive accretion. The star feeds chaotically from many directions in a crowded cluster. The disk orientation changes, so jets twist and wander. In SH-284, the opposite jet tips sit almost exactly 180 degrees apart, a tidy symmetry that holds for approximately 100,000 years of ejected material. That stable alignment matches core accretion predictions. It's powerful direct evidence that massive stars can form with orderly disks, not just chaotic flows. Jets like these are enshrouded in dust. Infrared light pierces that dust, and Webb's NIRCam delivers incredibly sharp views. That's why you see the jet's fine filaments and shock fronts so crisply. Pair that with data from ALMA in Chile, which spots cold, dense cores, and you get a multi-wavelength autopsy of how this star is assembled. SH-284's low metallicity mimics conditions in the early universe, when elements heavier than helium were scarce. Studying a massive star right now in a low metallicity pocket helps us test whether core accretion worked under those primordial conditions. That, in turn, feeds models of galaxy evolution, supernova feedback, and how the first generations of massive stars shaped the cosmos. Scale check. The distance from our Sun to the Alpha Centauri system is about 4.37 light-years. This jet is roughly twice that, like a double-bladed lightsaber carving across interstellar space. It's not moving at light speed, but over approximately 100,000 years, it's punched a path you can literally measure in light years. Webb's image gives us a tapestry of formation history and a strong case for core accretion in massive stars. The team also flagged another dense stellar core in the region that could be earlier in the process. So, stay tuned. There may be more giants loading their Roman candle outflows in this outer Milky Way lab. If this blew your mind, drop a lightsaber emoji in the comments. What should Webb zoom in on next? More massive jets or infant planetary systems? Subscribe and ring the bell for more space stories you can actually picture. I'm Name, see you in the next one.